I would like to inform you that this session is recorded. Um, can you guys use yesterday's link for attendance? Please mark your attendance. All right. So basically, we are talking about filters, active filters and passive filters. Uh, the passive filters are the ones without any active component. Active component means that they have some sort of a source, or there is something that can add energy or like power to the circuit. So just R, L, and C. And active filters are with op amps or transistors, right? So these are the ideal filters. I think we have discussed a lot on it, so we don't need to go in detail again. Low pass is low frequencies are passed, high pass is high frequencies are passed. Band pass is a particular band is passed, and band stop, as the name says, stops a particular band. Um, we can use this table. Okay, maybe we will use this table in analyzing the circuits later on. Okay, when we are analyzing the circuits, like what kind of filter is it, we will use this. We will be using omega 0 and omega infinity, and we'll see what is the magnitude and what is the corner frequency or cutoff frequency for that, the cutoff or the center frequency for that. Okay, so I think we did a lot. So the main idea is to find the transfer function. Once we have the transfer function in standard form, put omega 0, omega infinity, see what is the output. So you can see that if omega equal to 0, we get 1. For omega infinity, we get 0. This means this shows that this is a low pass filter. Similarly, and uh, we know that the half power frequency is the cutoff frequency. Half power frequency is when the magnitude is 1 upon under root 2. We have done this in the previous some of the previous slides. And then of course cutoff frequency. This is the formula. Luckily for low pass and for high pass, both the formula are the same formula, right? Once again, we found the transfer function. We put 0, we get 0. We put infinity, we get 1. This means it's a high pass filter. Band pass filter, basically, once again, we use the same concept. We find the transfer function. We put omega equal to 0 and omega equal to infinity. If we put 0, so this is 0 and this is infinity, so this will be 0. You can see if you put omega 0, this thing is 0. This is 1 upon 0 means infinity, and something upon infinity is 0. So for omega equal to 0, h omega is 0. It's for low frequency. Similarly, for high frequency, if you put omega infinity here, it will be something upon infinity. Something upon infinity is 0, and infinity is 0. So this is also 0. Something upon infinity is 0. So this is 0. This means if we go back to that table, band pass filter is 0 and 0 for both, and next we'll see that it's 1 and 1 for both, right? Where were we? Band pass. Okay, similarly band stop, we can just do the same math. So this is our procedure to proceed for the question, that we put omega 0, omega infinity, find the magnitude, then we can decide what type of filter is it. And once we have the type, we know that how to find the center frequency. Center frequency is the one at which the magnitude in this case is 0. For band pass, the magnitude is 1. Okay. Luckily, these are same for band pass and band stop, and 1 upon RC is the same for high pass and low pass. We don't need to remember many formula. All right, so this is the approach. Find the transfer function, find the magnitude as 0, find magnitude at infinity, evaluate the response, and then later on also find the frequency, the cutoff frequency and the center frequency. So you see we are finding the transfer function s equal j omega. We put omega equal to 0 and omega equal to infinity. we will see that in this case, when you put omega equal to 0, this is 0, this is 0, it's r upon r, means 1. Okay. Similarly, if you put infinity, infinity, something upon infinity is 0, so 0. This means this is a low pass filter. Right? Okay. The cutoff frequency is the frequency at which the magnitude of this transfer function, is equal to 1 upon under root 2. Okay, so we'll set this equal to 1 upon under root 2, or basically we take square, so 1 upon 2. So we already have R and L from the question. We can put the values here. We can simplify and we can find omega C. Yeah. Right. Any question? Any question, guys?
No, sir.
Thank you. Device settings, speakers. So let's go back to this one. Okay, so I'm not doing it. Let's see how we will proceed. Okay, we are given a circuit. We don't know what type of filter it is, although it is showing in the answer it is like this, but we need to find V naught over Vi in Laplace domain. So V naught is like those, especially those who are still not sure about how to solve it. I'm just doing it. I'm just walking it through with you, talking it through with you. So V naught is this voltage, which is also same as this. So actually, we want to find this voltage in terms of this. Whatever method we use, we can use node analysis as well. Let's say node analysis will be V naught. This is V naught. So this is also V naught. V naught minus Vi upon R1, V naught upon J omega L, and V naught upon R2. Right. So this is one way, and there is just V naught and Vi only. We just gather terms together in a way that we can find V naught on one side, Vi on the other side. We divide, so make a ratio, we will get the transfer function. Or simply, these two are parallel. Okay, we convert this into the frequency domain. So this will be J omega L. So R2 parallel J omega L is the impedance here, right? And if we're looking for V naught, we can apply voltage division. So the voltage here plus the voltage here is equal to V1, Vi, or we can say V naught is equal to R2 plus J omega L upon R2 plus J omega L plus R1 times V1, and this will go to other side in the denominator. So it will be V naught over Vi, right? Once we have V naught over Vi, it will be in terms of R1, R2, and J omega L. We will put uh, like omega equals 0 and omega equal infinity. We'll try to find out what is the response. When we will put omega equal to 0, we will see that the overall response, overall magnitude is 0. And when we will put omega equal infinity, we will see that 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 that, that, uh, that the magnitude is 1. This means 0 for low frequency and 1 for high frequencies. This is a high pass filter, right? How do we find omega C? Can someone tell me how to find omega C? Can someone tell me how to find omega C, guys?
Um, Please substitute the omega with
Substitute R and values into transfer function, then solve for omega C. Jocelyn, you're missing one thing, one very important thing. Yes, it should be 1 upon square root of 2. Thank you. So Justin and Hengqin, thank you very much. We will substitute the value of R and L in the transfer function. So whatever transfer function we have, and we will set the magnitude equal 1 upon square root of 2. It's like this one. So suppose we have the transfer function here, we'll set equal to 1 upon square root of 2 or take the square as 1 upon 2. So we'll do this. Substitute R, L values here, solve for omega c, we'll find the omega c. Right? Any one not sure yet? I wanted to see something. What is it? So the difference in active filters and passive filters is basically, once again, there are no inductors, mainly no inductors. So they are not very big and they cannot, they can add energy into the network. Okay. Normally the gain is not more than 1. In this one, we can have any gain. We can have like smaller circuits, less expensive, less in the weight as well, and many other benefits. So we will be using low pass filters. You don't need to remember these. If you know, that's good for you for your practice, what type of circuit there is. But basically it's about having the gain. This is the simplest structure. This is the amplifier. Do you guys remember the properties and how to find the voltages for amplifier? Like how do we write the equation for how do we get the transfer function equals ZF upon ZI? Can anyone tell me? Okay, let me ask some of you. Okay, where is the list here? Okay, Hafiz, can you unmute your mic and maybe answer a few questions? It's just recall. If you don't know, though, no problem. Hafiz, can you unmute your mic? Hafiz, is Hafiz here? Somehow Hafiz is not here. The only one I called is not here, or he ran away. Okay, Amirul. Amirul.
Yes, sir.
Okay, good. Do you remember op amps?
Maybe.
Okay, what is this thing?
Ground.
Okay, what is the voltage at this point?
That one is equal to 1, I think, or 0. 1, 1, 1.
1.
Yes.
The voltage here is 1.
Yes.
Okay.
Because
Anyone want to object, Amirul? Okay. Without going to 1 or whatever value, what is the relationship in the voltages here and here?
Equal.
Equal.
Yes.
So Amirul, what is the voltage here?
Oh, the ground is 0.
So this says 0.
So that one is 0 juga.
This is also 0. Okay. What is the current going in this branch? Or this branch?
V1.
I1.
No,
the current going inside here and inside here.
Sorry, sir.
Okay. There is no current going in this branch or this branch.
Oh.
Okay. So everyone, guys, the voltages at both terminals of an op amp is same, not necessarily 0, same. So if suppose there is a voltage source Vi equal 10 volts, it will be 10 here, then 10 also here as well. Okay. So this gives a hint that we can find the voltage at this node which is equal to this node, which is equal to 0 in this case. All right. We know for sure for a practical amplifier or ideal amplifier, there is no current going in this branch or this branch. So all the current which is coming here is going here. Okay. And what else? We don't know this current unless we have this current and this current available. So we can use KCL to find this current, but there's no way to find this current. All right. So if you want to find the equation for, I'm not carrying my surface today. Let me try to write it down. So we know that this is 0. Okay, let's call it for a time being V1. Can I write the equation at node 1? It will be V1 minus Vi upon Zi plus V1 minus Vo upon ZF equal to 0. All right. And since this is 0 and this is 0, we just get minus Vi upon Zi minus Vo over Zf, or we can say that minus Vo over Zf is equal to Vi over Zi, or Vo, or actually this one now. This is, we get cross multiply, we get this, right? So this is how we get the transfer function, and this is something that you may have to do if you're given a circuit like this. All right, so once we have the transfer function, then we can play around with other things. All right, so let me just take off all this scribbling. All right, so in this case, the same thing. We have this as ZF and this as ZI. ZI is in this case RI and ZF is the parallel combination of this. So we have ZF and ZI available. We just put them here to get the transfer function. So we get the transfer function like this, and we can confirm that if omega equals 0, this is 1, and just remaining minus Rf upon Ri. And when omega equal infinity, 1 upon infinity is 0. So this means this is all is 0. This means this is a low pass filter. Okay, and this is similar to the passive low pass filter. As if you remember, this is what the passive low pass filter look like, except this additional minus Rf upon Ri. So when omega equal to 0, we have a gain of minus Rf upon Ri. So this is how, once again, this is the way we. So if I want you to find out the cutoff frequency of this low pass filter, we will do the same thing, that we will set the magnitude of this equal to 1 upon under root 2, and we can find the cutoff frequency, which in this case is 1 upon RFCF. We'll find out. Right. Same is the case with the high pass filter. Somehow they're opposite. Oh, I checked yesterday as well. No, nothing. So similarly, we just proceed in the same way, and at infinity, this will be 0. This will be 1 at infinity, actually, infinity upon infinity, kind of 1. And except that we'll have a gain of minus Rf upon Ri. All right, so same story for band pass. So the band pass we can make using cascading low pass and high pass filter with the inverter. Again, the same stories. We are interested in omega naught in this case, which is the center frequency, and at center frequency we have the maximum amplitude. We can find it using the same concept. right? This is the whole transfer function of the band pass filter. So this is low pass, high pass, inverter. And the corner frequency for the low pass section, that this section is in this case omega 2. By the way, like omega 2 is greater than omega 1, as we can see, but the greater one is belonging to the low pass and the smaller one belongs to the high pass. This is like common sense. Just bifurcate this figure. Bifurcate this figure, you will see that this is a high pass section and this is a low pass section. So we'll get the values from the low pass and the high pass. You can see that this is coming from this one and this one is coming from this one, which actually was in this case C1R, C2R, like that. Okay, yeah, these values luckily remain the same. Omega naught is square root of omega 1, omega 2. Bandwidth is omega 2 minus omega 1, and quality factor is omega naught upon B. These are like, part C and part D. Find the bandwidth and the quality factor also, but main thing would be something like that. All right, how to find the passband gain is use the center frequency. Remember, I just told you that at omega naught, the magnitude is K. The magnitude, if you want to find this magnitude here, it will be at omega naught. This shape could be sometimes maybe like this, but the maximum amplitude is at omega naught frequency, right? So what is omega naught? We know omega naught is equal to under root omega 1, omega 2. So we have omega 1, omega 2 from here. We'll use it to put it here and then evaluate using this omega naught in these and these values. This is what we have done here. So this is the expression. This is omega 1, omega 2 already here. We replace this omega and this omega and this omega with omega naught, which is this, in this case, this one. You can see omega naught, and omega naught. We replace it here. We'll get the passband gain. Right. So I think for the quiz, expect something like maybe I will give you the transfer functions for low pass, high pass, maybe band pass as well, and I'll ask you to design a low pass filter. Oh, sorry, a band pass filter, something like this. Design a band pass filter for a particular frequency, or find the frequency for. So you will be like plugging in the transfer functions, taking the values from there and placing them in place of omega 1 and omega 2, and the rest is just calculation. Same story here, except that previously we were multiplying the low pass and high pass. This time we're adding the low pass and high pass. Okay. Yeah. So this one is low pass, this one is high pass, and this one is the adder circuit. This is all from your op-amp from circuit theory. Okay. Luckily, we are lucky that we still have the omega 2 and omega 1. Low pass one and the high pass one is still the same, and same formula as well. And gain in the two pass bands at omega, like low frequencies and high frequencies, the gain is RF upon RI. Okay, so in this question, do we have a okay? Design a high pass active filter with a high frequency gain of 5 and a corner frequency of 2 kilohertz. Use a 0.1 microfarad capacitor in your design. So you see in the previous question, it was designing a low pass filter with a DC gain of 4 and a corner frequency of 500 hertz. We are given the frequency. So from this frequency, we can find the omega C in the next question as well. High pass filter. We can find using this 2 kilohertz the omega C. Okay, and the omega C itself is 1 upon RFCF, so that is the same there as well. Luckily in this case we are given 0.1 microfarad capacitor in your design, so we have this capacitor. You will find the RF using this formula because we have 2 kilohertz here, 2 kilohertz, 2 pi 2 kilohertz equal to 1 upon RFCF. We have CF, we can find RF. And yep, what else? That's it. Yeah, same thing. So easy questions. What is the most difficult thing that you would expect is, suppose I give you this circuit, for example, and I tell you that the transfer function of this is this, transfer function of this is this, and the transfer function of this part is, where is it? This one here. Okay, I can give you the individual. Maybe I'll put them separately. I'll put them separately. I'll keep this part not connected. I'll keep it like this, separate circuit. This is another circuit, and this is another circuit separately. Okay, I'll ask them. I'll ask you to connect them in a way to design a low pass or a band pass or a high pass. Maybe with these three, I can ask you to design all 4 circuits using these 3, by the way, right? And for one of them, I'll ask you to find the cutoff frequency or the corner frequencies or things like that. This is the most difficult that I can make for this particular topic. Okay, I'm not going to ask you to find the expression of all these. I might be giving you already, but how to place them properly is the hint is actually here. This one or like this one. This is the band stop. This is the band pass. Where is it? So this is the band pass. So you have to understand the concept of the band pass and band stop, how to place them, where to place them, and I think that should be enough. All right. And for scaling, it's just using some formulas to change the, where is it? So these are some formulas. Actually, this is the summary of scaling. So the scaling changes, normally we design a circuit with standard values unit, and later on in some of the other courses you will also go for per unit quantities, but not right now. You design a simple circuit and then you can scale it to any level. Okay, so for the basic circuit we just keep R and C and L1, and then we can scale it to another level, and these are the formula. The good thing is for just scaling, the omega remains the same. The frequency does not change, right? And in frequency scaling, what was that? Yeah, R value is not affected because R does not have frequency. R does not depend on frequency. Okay, although L and C will change. And this is for simultaneous magnitude and frequency scaling. So I don't know if I'll give these formulas to you or not. I'm not sure right now, but I might not give the formula for these. So in a given circuit, the fourth order I mentioned yesterday, although it's not important at this level, the order of the circuit is determined by the order of the denominator. S square is quadratic or second order, S cube is third order, S to the power 10 is 10th order. And just to give you some flavor of what this does, if suppose this is a first order filter, low pass, this could be a second order filter, this could be a third order filter, this could be a fourth order filter, and this could be a 100th order filter. Understand? We are complicating the circuit hardware, and with that we can achieve better shape of the magnitude response. So of course this is not a good filter because it is only letting very small, although the cutoff frequency is somewhere over here, but it is deteriorating, attenuating the amplitude here. So maybe you get 0.8, 0.78, 0.81, which was supposed to be 1. Supposed to be 1 until maybe yeah, this level or whatever the frequency is. So these lines, which is very messy actually, but we can enhance the magnitude response by increasing the order. Can I find some? Where is? First order low pass filter. See, this is very lousy, but third order low pass filter. I think this is a good example. Can you see this figure? Let me just copy it. Where is it? Where are we? Okay, so you can see that this is first order, so very lousy. Second order, better. Third, even better, and so on. See, this n is 1, 2, 3, 4, 5, 6, and if we go to infinite order, it will be like this. Okay, so this is a low pass filter with different orders. At the moment, you don't need to worry about it. All right, what is the question? Okay, omega C, it is designed to operate at cutoff frequency of omega C1. Scale the circuit for a cutoff frequency of 50 kilohertz. So from 1, don't get mixed up with radian per second and hertz or kilohertz. All right. So basically, this is the frequency that we want to operate at, omega C prime 2 pi 50. It was actually 1 radian per second. So we can find the Kf, the factor that changes everything, by the ratio of the new frequency upon the old frequency. We get pi to 10 to the power 5. And there was 1 resistor, 1 ohm resistors. So we can find, actually, if it's, it could be actually any resistor. We mentioned yesterday, it could be any resistor. Just put that resistor value here, and yeah, we just okay. I thought I figured it out, but okay. Let me see if I can find a question in which they have like 2 different types of, because if for that we need to find Km first. So the Km is 10 to the power 4, and then only we can. So if we have 2 different resistors, 1 ohm and 2 ohm or 5 ohm, then do we need different Kms? I'm not sure right now. I don't claim anything wrong. Okay, once we have Km and Kf, we'll use these scaling formulas to get new values, and L1 prime, L2 prime, C1 prime, C2 prime, and that's it. I think this is the relaxed topic that we are doing right now, because next week we have Fourier transform, so I'm excited for that as well. Any question? So this was just a review, and I'm sorry I couldn't compile the questions for you guys, so I'll do that. A lot of things about this course happening in preparing your tests and grading and final exam also. So yeah, your test 2, by the way, will be in week number 11. Okay, not week number 10. I'm going to take your test 2 on during week 11 after the class. So not on Monday, maybe on Thursday or Friday, probably, so that you have ample time to prepare, and it will cover until the week 11's material. Okay, so get ready. So it will be from whatever we left off in test 1. So test 1's material will not be covered in that, but all that covered after test 1 until week number 11 will be. So week number 7, 8, 9, 10, 11. It's quite a long. Okay, until week 10. Until week 10, whatever we cover from week 7 to 10, or after the test 1 will be covered in test 2. All right, so this weekend I'm going to take 2 quizzes. One quiz will be on board plot. I might give you a transfer function, and there will be like 2 questions. One is I'm giving you a transfer function, and then you have to draw a board plot and upload it. And the opposite is I'm going to give you a board plot, and you would have to find the transfer function. Interesting. Let me show what I mean by that. Problems. Okay. All right. So let's say I'll give you this board plot. Okay. Remember, each line means something. Each line means something, that okay, initial constant, if it is coming in the beginning, this means that this is the constant gain thingy. If something is going up, means there is a 0. If something after the first constant, this means there is if there is a flat line, this means this effect of this 0 is being cancelled by a pole. So this plus 20 dB, minus 20 dB. So this is happening at some particular frequency. All right, and then so like, can I say that for this particular one, this is this value was equal to 20 log of that constant, right? 20 log of this constant. So if it's equal to 20, what is 20 log of f? What is x if it's 20 log x equal to 20? What is x if it's 20 log x equal 20? So since the magnitude is 20, so 20 equal to 20 log of x. So what is x equal to? Has somebody answered? I'm not sure, because okay, I missed a few. 0 was about something else. Okay, 10. Yes, thank you, Hengqin Tian. Yes, x, if this is 10, this means 20 log 10 is 20. So this means that k equal 10, right? So okay, now we see that there is something like a plus 20 dB per decade, is it 2 to 20? So 2 to 20, there's an increase in the slope, which shows that when do we have an increase in slope? When we have a 0, and it starts at 2. This means a 0 at omega. I'm using this W equal 2, right? And this is going until 20. After 20, this plus dp is somehow cancelled. Can I say that there is a pole at omega equal? What do you think? What do you think? Omega equal? Anyone? Where do we have a pole at? This line is showing that there is a 0 at omega equal to 2 because this kept on going until the frequency 2. At 2, we notice that the magnitude is like rising 20 dB per decade. So this is 20 to 40. Okay, this means we have omega equal 2. There is a 0 at 20. This increment is cancelled out. So there must be a pole here, and here means at 20. If somebody wrote something, nobody wrote something. Okay, what happened after at 100? So it kept on going like this. At 100, there is again a decay, minus 20 dB per decade. So can I say there's another pole at omega equal 100? Right? So can I say in a way that this is something? Can I insert an equation? What is the equation? Equation that h omega is equal to, first of all, make a fraction. Okay, what will be there? It will be a 10, and then there is a pole at 2, so 1 plus j omega divided by 2 plus. Are you all following? Are you all following, guys? Can I see a raise of hands if you are all following? Wow, that's fast. Either you are good students or I'm a very good teacher. I think you're good. This time I'm lucky that I have good students. I'm sure. All right, thank you. And in the denominator will be, where is it? How can I go down there? Will be a pole at 20 and a pole at 100. So 1 plus j omega by 20 and j omega by 100. So we got the converse of the problem. Converse meaning the opposite. How can I fit everything? Okay. So this could be another thing to find out, and I think I can make MCQ type question or not. Maybe some question about MCQs as well, because we are missing out on some of the theories. And for me, at least for me, at this time, magnitude response is more important than phase response. So probably I'll take the part in which you have to draw the board plot. I would be asking you to plot the magnitude and phase, both responses, but the opposite, I'll just keep it this way. Only the magnitude response. All right. And so shall I keep the quiz back to back same day or one on Friday, one on Saturday? Some Nazir Mubin is asking that do we need to convert the omega to S? Not necessary. If you do it, no problem. If you don't do it, also no problem, because unless it is specified, find the transfer function in omega domain is okay. Okay. Okay, any question? Okay, so I'm going to post the questions just like the previous ones. And since we couldn't do the problems here, I'll give you more time. So you have the time until the quiz. Before the quiz, you have to submit the video solutions. So one quiz. So quiz, I believe 5 on board thoughts Friday. Let's set it 9 p.m. Is it okay? And quiz 6 on filters. Okay, let's do it Monday to give you enough time. Monday, 9 a.m., which is my time as well. So video submission before Friday 9 p.m. for before is it okay? Any question, guys? I'm going to post the questions by today, hopefully. Tonight, hopefully, inshallah.
Yes, sir. There's two now. There's really two video submissions for two tutorials.
Yes.
Okay, so are we receiving the tutorials, both tutorials today, sir, or we receive the both point tutorials for now? The other tutorial another day.
Come again?
No, sir. Since one is on submit before Friday and one submit before Monday.
Yes.
So that do we receive the both tutorials today?
Yes, you will get the tutorial today, inshallah. You'll get the questions today for both of them. And for the board plot, you have until Friday. For filter, you have until Monday.
Okay.
Right?
Okay.
Anyone else? Any question? One more thing. I think I need your voice feedback maybe as well. Since somebody asked me, I think Arif asked me or someone else about the next week. How many of you are like traveling for the Raya Haji? I don't know if you guys do that or not. Because somebody asked me to, like, will we be having class on Monday, the after Raya Haji? I'm stopping the recording here because we are done with the tutorial. I'll post it.